All right, welcome back to part 2 of Ohm's Law. Electrodynamics strikes back. Yes. Okay, so we just looked at the general form of Ohm's Law. The current density is proportional to the applied electric field with a constant of proportionality given by the material that the charges are flowing through. Okay. So now let's start to ask some questions about materials and see if we can get some more information about current from the current density. All right, example problem number 1. A cylindrical resistor with cross-sectional area A. Let's draw this. I am a cylinder, sort of. So cross-sectional area A and length L. Is made from a material with a conductivity given by a Greek letter sigma. Cool. No numbers needed here. If potential is constant over each end and the potential difference between the two ends is V, V. What current flows? Classic physics problem. Where are the numbers? We don't need numbers, it's fine. But we do need to define our axes. So we're going to say that that's the z direction because I drew it sideways, and that makes my life easier if I draw it like that. So the first thing that I'm going to claim, which is true, but we haven't proved it yet, but is that the E field is uniform within this material. And that's helpful. So we have an E field flowing, pointing this direction. E fields don't really flow? I don't know. That's a good question, actually. For another time. So the current is equal to the charge density times the cross-section or the area that it is flowing through. And in this case, the current is flowing through the cap of our cylinder. So that equals the charge density times the area, or jaw for short. And so in this case, we can use this equation for the current density. And so we get sigma times the electric field times A. And for a cylinder where the E field is uniform, we have to replace E because technically we don't know E. So we have this conductivity times the potential difference divided by the length times the cross-sectional area of our resistor. Boom, that's it. Pretty easy peasy. So really all this is doing is just taking this general form of Ohm's law and leveraging the fact that we know some information about the potential difference within a cylinder based on prior work with electrostatics. Cool. Okay, so this is example problem number 1. What I am going to do is I'm going to write in the corner I1 equals sigma V over L times A. Okay, so we're going to set that aside and we'll come back to it after we do example problem number 2. Okay. Example problem number 2. Here we go. 2 long cylinders. Ooh, fun. Of radii A and B. Okay, I'm going to do, you know what? We're going to use colors for this. Yeah, what's up? Okay, so cylinder number 1. Cylinder number 2 is going to be blue. And I lost my blue chalk. Okay. Yeah. Okay, cool. All right, so this has radius B, and the inside one has radius A, little a. They are separated by a material of conductivity sigma in between, so I'm just going to put that there. If they are maintained at a potential of V, difference V, so we have V between here. What current flows from one to the other in a length L? So we're going to set this length to be L. And we have the E field is pointing up like this. Okay, so the field between cylinders. This is something that we can look up. Yeah, what's up? This is why our work in electrostatics was important. I didn't cover all of it, but these are definitely things that other folks have figured out. And we like to be lazy. Okay, so we have a charge per unit length on the inner cylinder. That's what this lambda is. Divided by 2 pi epsilon naught s in the s hat direction. And so quick refresher in cylindrical coordinates. This is the z direction, and this is the s direction, and then you have the angle going around. I'll just try to draw that in the azimuthal direction. Now the current in this case, we need to sum up over all of the contributions of the current density. It's not the caps in this case. So we have J times dA, and we're going to replace current density with the electric field. So we can pull out sigma, and we have E dot dA. And now we need to take a second and look at the geometry of our situation. And we note that, what area are we interested in here? I'm running out of space. So I am going to just really quickly, we have cylindrical coordinates, but not all of the cylinder is contributing to the current. Specifically, the dot product pulls out the parts that are not perpendicular. So anything that is perpendicular to E will not contribute because the dot product is 0. Two vectors that are perpendicular give a dot product of 0. Ooh, excuse me, chalk's making me sneeze. And so in this case, the two ends of the cylinder do not contribute, and we only have the round part of the cylinder, the wrapper, if you will, or the body of the cylinder that contributes. And so we can pull out, once we understand that, we can pull out the magnitude of E and integrate over the appropriate area of the cylinder. And hopefully you remember this, or you can either look it up, but the area of the body of the cylinder is 2 pi SL, again, where S is this kind of general radius. So S is kind of somewhere in here. It starts from here and goes to there. But we want to just generalize it for now. Okay, and so then when we plug in the magnitude of E, the 2 pi S cancels with the 2 pi S here, and so we just end up with sigma, how did this book write it? Sigma over epsilon naught times lambda L in the S hat direction. I guess we don't need that. Okay, fine, whatever. Okay, cool. So, do we need that? Yeah, we need that. We're going to put I2 over here. Well, that kind of smushed together. I2 equals sigma over epsilon naught lambda times L. Okay. And I need more space on my chalkboard, so I'm going to erase this. Okay. And now, let's look at the potential difference. Woo! V! What's up, V? Okay. So the equation for this, we're going from B to A, E dot dl. And so we're going to plug in E here. We have a negative lambda over 2 pi epsilon naught from B to A. Okay, and again, this is where we have to talk about the geometry of the situation and what path length are we following. So dl in cylindrical coordinates, I actually will pull this one out, since it can be a little trickier. We have ds s hat plus, I'll put it down here, plus sd phi hat plus dz z hat. Okay, and so in the dot product, again, both of these are 0, and this is the only direction that contributes, because everything else is perpendicular to the E field. Okay, so we come back, and so then that means that our integral is just 1 over s ds. And we end up with a negative lambda 2 pi epsilon naught ln of s from B to A. Ooh, that got smushed. Why is there a stray W there? Hey. Okay, bye. Okay. That might be a little small. I apologize. Okay, and then we really just, it's funny, I'm looking at my notes. We really just plug in A and B here. So we end up with negative lambda 2 pi epsilon naught ln of A minus ln of B. We can smush these together so that it's ln of A over B, but I want to get rid of this minus sign out front, so what we're going to do is just swap them and get rid of that minus sign. So we have lambda over 2 pi epsilon naught ln of B over A. Okay, let me just double check. Cool. Okay, so in this equation, the only thing that we don't have any information about from the problem is lambda, or this charge per unit length on the inner cylinder, this one. So we need to replace lambda in this equation with lambda from the potential, aka we just solve for lambda. And so we get lambda equals 2 pi epsilon naught V over ln of B over A. Okay. And then, ooh, we're in the final stretch. Here we go. Okay, so now we have the current. We can plug this back in for the current, and we get 2 pi sigma. Epsilon cancels. We have an L, and on the bottom we have ln of B over A times the potential difference, or the voltage. Cool. Okay, so now this is I2, and we have I1 equals sigma. I'm going to rewrite it, and we'll see why in a sec. Okay, and so now I'm going to bring back my colors. Hey, what's up? Oh, look at that. Okay, so if we look at both things in the parentheses, square brackets, square brackets, these are all constants that depend on the geometry of the situation, the length of our cylinder, the radius of the cylinder, aka kind of the separation distance between them, and in this case, the cross-sectional area and the length of the cylinder, geometry, the shape of the object through which the charges are flowing. Cool, that makes sense. And we also have this constant that depends on the type of material that the charges are flowing through. Cool, that also makes sense. So we could look at this and we could say, wait a second, this is just a constant that depends on the situation at hand. So we could write a more general form of this equation of V equals I times R. Woohoo! There we go! We made it to Ohm's law. This is really cool because this tells us that the total current flowing from one electrode to the other is proportional to the potential difference between them, and it's proportional depending on the resistance between where the charges started from and where they're ending. And so what's really interesting is that what we found from here is that we kind of are defining this term based on the fundamentals that we know about current density, potential difference, and the electric field that we learned a lot from in electrostatics. So what we know about resistance is that like I said, it's a function of geometry and the material properties. And it's basically been set to be measured in ohms, or OMS, with this fun symbol. And it is volt per ampere. Let's say volt per ampere. Cool. So we kind of already knew about these, but this is new. Fun! This is also really powerful because this tells us if you want to double the voltage or the potential difference, then you just double the charge everywhere. That doubles the electric field, that will double the current density, and that will in turn double the current. Yay! One caveat, I'm not going to get into it in the weeds too much, but I do want to say that this isn't a, this is more of, Ohm's law is more of a rule of thumb. It's not true everywhere in all situations. It's not like some of the more fundamental laws like Gauss's law or Ampere's law. And so just keep in mind that if you're dealing with very specialized circumstances, Ohm's law may not apply to your situation. It's not necessarily new physics, although that's really cool that you're working in a specialized situation. So yeah, very handy. I use this equation all the time in electronics, and I think that it's super cool to work up to where it comes from. All right, I'm gonna put down my chalk and dust my hands off. All right, we made it. We got to Ohm's law. There's some other really cool topics in electrodynamics that I'm going to cover. Please let me know if there's anything in particular that you would like to learn about or example problems you want me to cover. Yay! Thank you so much for watching, lovely humans. I will see you next time. Bye!